Loop quantum gravity is a theory that tries to explain how the universe works at its tiniest levels, and it does so in a very different way than other theories like string theory or general relativity. Imagine you're trying to paint a picture of a landscape, but all you have is a very small brush that can only paint tiny dots. You start painting and realize that the picture you're creating is made up of thousands of tiny dots, each with their own color and position. You might even start to see patterns emerging as you connect the dots. This is a bit like how loop quantum gravity works. In loop quantum gravity, the universe is made up of tiny dots called loops or spin networks that are so small that they can't be seen even with the most powerful microscope. These loops are constantly moving and interacting with each other, creating the fabric of spacetime that we experience. One of the big differences between loop quantum gravity and other theories is how it handles gravity itself. In general relativity, gravity is seen as a curvature of spacetime caused by massive objects like planets or stars. But in loop quantum gravity, gravity is seen as a force that is transmitted by particles called gravitons. These gravitons are constantly being exchanged between the loops, causing them to move and interact with each other in complex ways. Another interesting thing about loop quantum gravity is that it suggests that there is a minimum size that anything in the universe can be. This is called the Planck length, and it's about 10th to the power of minus 35 meters. This means that if you were to zoom in far enough, you would eventually hit a point where everything is made up of these tiny loops. So why is loop quantum gravity important? Well, for one thing, it could help us understand some of the mysteries of the universe, like what happens inside black holes or what the universe was like in its earliest moments. It could also help us reconcile quantum mechanics, which describes the behavior of subatomic particles, with general relativity, which describes the behavior of large objects. One of the key challenges in combining these two theories is that quantum mechanics treats spacetime as a fixed background, while general relativity treats it as a dynamic and fluctuating entity. Loop quantum gravity resolves this tension by treating spacetime itself as a quantum object that is made up of tiny loops or spin networks. These loops are constantly interacting with each other, creating a web-like structure that represents the fabric of spacetime. Another challenge in unifying these theories is that they have different ideas about how time works. Quantum mechanics assumes that time is fixed and absolute, while general relativity allows time to be influenced by the presence of massive objects like planets or stars. Loop quantum gravity resolves this tension by treating time as an emergent property of the interaction between the loops. Finally, loop quantum gravity also suggests a discrete structure for space and time, rather than the continuous structures assumed by general relativity and classical physics. This discreteness is related to the idea of the Planck length, which is the smallest length that has physical meaning in loop quantum gravity.